Hello everyone, welcome to another lecture of digital signal processing. So in today's lecture we are going to start our new topic on digital filters. So in the first digital filters we are going to see about FIR filters followed by your IIR filters. So FIR filters stands for finite impulse response filters. So we are going to see what are the properties of FIR filters and what do they represent, and what are their types of FIR filters, and what do these FIR filters imply in terms of functionality. So basically the entire class is an intro lecture about your finite impulse response filters. Alright, good. So let's see more on these. So before we do that, let's see some of the properties of your FIR filters that are unique to these filters. So you know by now the FIR filters are a class of digital filters, and when I say a class of digital filter, they are the DSP filters, right? The digital signal processing filters, and most of the DSP algorithms are filtering based. So they work with filtering based. So what I can say is these properties which we are seeing as an FIR property, they are unique to these FIR filters, and also they define them as a DSP filter. Okay, these properties define this FIRs as a DSP filter. So the first property is your FIR filters are a frequency selective filter. So they can either be used for frequency selection, or they can be used for frequency identifying the frequency patterns. So mostly they work with the frequency of your signals. The next one is they are an LTI filter. So they are based on your linear time invariant property of your DSP. Then your FIR filters are causal filters. So we'll see what it is to be causal. Then your FIR filters are an all zero filters. Then your FIR filters have a linear phase response. So these are the 5 properties: causality, zero dominance, linear phase, LTI, and your frequency selective. So except the LTI, I'm going to discuss all the other 4 properties in detail, because LTI is something we have already covered in the previous lectures of digital signal processing, and it is the same thing. So what I can talk about FIR filter is they are LTI and causal. So we will see the causality part. So when I am talking about causal, you know that anything that is not dependent on the past values, right? So they are your causal systems, and in this case for FIR filter to be causal, the condition that I'm going to be stressing on is h of n is equal to 0 where n is less than 0. So when my h of n is equal to 0 and at n equal less than 0, it means that for the the negative samples, when n less than 0, you're talking about the negative samples. So your filter must not have any response, so which means your filter is more or a positive definite filter, right? So now let's see how this is realistic. So now if I have a filter which is a convolution of my input x of n with my h of n, where h of n is your FIR filter, then I have in a frequency domain it is x of omega into h of omega, and now my h of omega, which is my FIR filter in frequency transform, is given by sigma h of n e to the power of minus j omega n. So now let me just put some values for n, which is from minus 2 to plus 2, just to show you that what my causality is, how my causality is implied in this h of omega. So when you see this expansion, I am having h of minus 2, h of minus 1, then I have h of 0, h of 1, and h of 2. Now this is a non-causal system, because my h of n is not 0 for n less than 0. But if I have to convert this into a causal system, what do? Is I get rid of that 2 values which are n less than 0. So that is n equal to minus 2 and n equal to minus 1. So if I get rid of these two index values, now my system without these two, or my filter, is a causal filter. Good. So when n was between -2 to +2, you have a non-causal filter, and when I make n between 0 to 2, then you have a causal filter. It's very simple. It's like we are seeing just the one of the causality property for an FIR filter, and that should be enough at your undergrad level. So this is how you define causality. So now any signal can be converted from a non-causal to a causal form, right? So which means if I am having a FIR filter which is non-causal by definition or by mathematical modeling, I can definitely find ways to convert that into a causal representation, and then I can use them. Alright, so this is okay, we will be seeing later on in FIR structures. So we will be seeing some filter structures for FIR, and there I'll be telling you why this causality is an essential condition for your FIR filter. Alright, so because it comes in the realization of filter structure. So when you want to convert these FIRs into an actual hardware prototype, and there you have the realization problem where you cannot use that non-causal terms. So we'll be seeing that in the coming lectures. For now, I can just we'll just talk about the intro of causality, or just we'll see at the definition of causality, and also know that your causality is an essential condition for your FIR filter. The next property that we have here is FIR filters are primarily zero dominated. So this is like contrary to your control systems, where you have a pole dominated system. So your control systems all work with S plane, and your characteristic equations are the denominator, right? If you remember your control systems at least a little bit, you know that the characteristic equations in your control systems comes in the denominator, and they are pole dominated. But your digital signal processing, especially your FIR filter, so I will come to IIR filter later, but for FIR filter you can say that your FIR filter is zero dominated, because you have, this is the structure, this is the function model of your FIR filter, and you can see by simplification I have 3 zeros in the numerator, and then I have a pole which is equivalent to 0, right? So this is you can say this is a pole at origin, or your pole is equal to 0. So that is why many of the textbooks call your FIR filters to be an all zero filter, because your FIR filter is represented by this typical equation. The standard representation for your FIR filter is using the Z transform, h of n into z of minus n. So in signals and systems you have seen what is Z transform stands for. They are a pole zero representation. So that is what we use for your FIR filters also. So modeling of FIR filter, you can say it is just h of n into z to the power of minus n. So the next property was your frequency selection property. So this comes from the fact that I have my e to the power of minus j omega n, because that is my z, and when n is 0 to 2, that is my causality, and this is the zero dominated. So we have seen these two properties thoroughly. And the third property we are looking at is FIR filters are your frequency selective filters, which means if I set the value of omega from 0 to pi, then I am telling that my frequency, my filter is active only in that range between 0 to 5. Got it? So that is how you make your FIR filters work as a frequency selective filters. And you can also have a frequency emphasized filter. So what you can do is, between this 0 to pi frequency, you can enhance, you can make your signal better, you can boost your signal, right? So there are a lot of things we can think. We can increase amplitude, and you can change the phase, because these are the three parameters we work with: amplitude, frequency and phase. And you can do, you can modify any of these parameters when you are in a particular frequency band, which in this case is 0 to pi, right? That is a frequency selection that we are using. And a response function, the response characteristic is shown here. So the response characteristics for h of omega to be from 0 to pi and 0 elsewhere is shown in this graph. So the next is we are going to see now this response characteristic we are going to see in detail for some of the basics. There are like 4 standard filters that are used almost like they're like the very common filters that you see whenever you have a DSP. So it is very simple. You have used in communication, we use this low pass filter because our audio signal, the voice that we are using is a low pass signal or a low frequency signal. So a low pass filter will help make that to help allow the audio signal to get through to your phone. So what happens is when you speak and you have the surrounding noise, suppose you say your fan is switched on, so the sound from the fan is high frequency but your audio is comparatively in the low frequency range. So if I am having an LPF filter in my device, what happens is this sounds from the fan will get filtered because that is a high frequency sound. So that can be easily implemented using your FIR low pass filter, so which passes all your low frequency. The complement of an low pass filter is your high pass filter, which allows all the high frequencies to pass through. So when you have a high pass filter, the response characteristics is just the opposite to your low pass filter, and your high pass filter can be considered for the same example. You have your voice and you have a fan sound. So if you want to keep the fan sound, you use a high pass filter, and if you want to keep your voice, then you use a low pass filter. Got it? So high pass filters and low pass filters are very useful. So most of the time you can use a high pass filter to extract the high frequencies, and then you can, so there are many applications, flicker removal, jitter removal, because these kind of jitters, flickers and kind of whatever the spikes that you see, they are like they are going to have a strong frequency component, or they are coming in the higher band, frequency band. So a HPF will allow you to pass that and then keep the rest, so that you can it's like considered as a filtering mechanism. So the next 2 common filters are your band pass and band stop filters. So this is very much what is used in this modern day communication, because now you are giving a band of frequency. So your TV channels, so let us say Star Sports 1, Star Sports 2, Star Sports 3. So they are all having different frequency bandwidths, right? They are given more like bandwidth. So it is the same thing. So here my Star Sports will have a filter that will allow omega L to omega H frequencies to pass through its station. So which means that is the band that my frequency selection happens. So that band of frequency between omega L and omega H passes through, and the rest all frequencies get blocked. Now the complementary to your band pass filter is your band reject or band stop filter, which does the opposite. It just doesn't allow a band of frequency, and it passes pretty much everything through. So that is your band stop. So you can think of band stop as 1 minus band pass, and your HPF high pass filter to be 1 minus low pass filter, where 1 is your all frequencies. Alright, so something like this. So that is your band stop filter. And what I have shaded, these are called as my pass band. I didn't write this before because I did here, it's where the band concept is coming. So this is my pass band here, and where the frequencies are getting blocked or not sent through, they are called as the stop band. So that is your stop band, and then you have your pass band, and these are the 4. So these are the 4 common filters: low pass filter, high pass filter, band pass, band reject filters. And their function responses only, it defines the frequency range, right? The other magnitude response is h of omega is 1, so only the frequency range is defined for that. So next most very important property of an FIR filter is a linear phase. So we have seen few properties that are that are very essential for your FIR filters to function. So the next important property that we are going to see is linear phase in FIR filter. So when I say I am having a linear phase, what do I mean is the FIR filters allow the input reaches the output. So when you have an input signal, it is sent to an FIR filter and you get an output signal. So your output signal is going to be having some delay because there is a processing time. The filter has to process the input, right? It works on the input and then it gives it to the output side. So there is some delay in in you getting the output. So it is, and what happens in case when I say it is a linear phase, FIR filters have a linear phase, this delay is constant throughout. Suppose this is very very important because you are sending a signal. So you are sending a signal at a certain frequency, and then your FIR filter is processing it, and then you are getting an output. So when I am talking about constant delay, which means your phase change it's also constant. So which means it's only dependent on the frequency and it is very constant, which means the delay is constant throughout all the frequency ranges. And this is very very important because if I am having variable delay at variable frequencies, then I am having big problems because your phase is just phase and frequency are reciprocative, right? So you the derivative, they are more, the derivative of your phase is given as the frequency. So which means when your phase is not constantly changing or it is variably changing, then your frequency is also gonna get altered, which means the filtering itself will change the frequency of your output. It should not happen, right? So when I apply an FIR filter, that should not change the characteristic of my input signal, and that is taken care by this linear phase. So you see here the delay is what is introduced by my filter. So my filter e to the power of j n0 omega introduces just a delay x of n minus n0. So we will see in detail because this phase is important. So what I meant to say was this delay, right? So this delay n minus n0 is going to make sure that my FIR filter is operating on the input signal and it is producing an output signal, and the frequency of the output signal is not it's not different from the original signal, and it is not different at different places. So that is what this linear phase ensures. So that is very very important because which means your filter is going to have a property that can be used on an input signal, and it can produce an output without altering much about the without varying the frequencies at different times. So let us see now this delay can be represented. So now the frequency representation is something I can write as a magnitude and a phase characteristic. So your h of omega is equal to magnitude of h of omega into e to the power of j theta omega, which is your phase. Okay. So the linear phase is now your theta omega. So comparing this with my above equation of h omega, I can write my theta omega, my magnitude is a, and then my phase is minus n0 omega. Good. So now you can see this when I say this is a linear phase, what I can say is that n0 is going to be constant. So that n0 is the delay term, and your omega is the frequency of your input signal. So which means your FIR filter is going to have a phase of some constant multiple into that frequency, and that is not going to be changing much because it is not dependent on your input signal. So this omega is fixed for your input signal because your signal is having a certain frequency. If it is a periodic signal, definitely it will have a certain frequency, and then we are having this minus n0, which is a delay, and that delay is also going to not change. That n0 is going to stay fixed throughout this FIR filter operation. And now from this phase I am writing two variables, phase delay and group delay. So what I meant to say is this N0 is nothing but a delay in your phase. So your output will appear after some time because the processing between the filter and input takes some time. So the filter will process the input and send it to the output, and that's going to have a delay, and that is your phase delay. And your group delay is something which we take it as a derivative, and group delay is also N0. And what it means for a group delay is, group delay applies to an envelope of signal. So when I say it means that in case of your amplitude modulation, that is a perfect example. So your one cycle of sine wave is encoded with a carrier signal, and that one envelope is together will have a delay of N0. Understood? Because it processes, the amplitude modulation processes the sine wave, and when that is a message signal, and the message signal will have a total delay of N0. So that is your group delay. It applies to the envelope or your range of a signal. Okay, so pretty much they are the same. You can just think phase delay and group delay are the same, just the difference in formula, but the output is N0 for both. So that is what your linear phase brings, and your nonlinear phase leads to unpredictable filter response in terms of the frequency. So if you have a nonlinear phase, then what happens is your output will be coming. So there is a delay of 10, there is a delay of 12, there is a delay of 14, and which means whenever there is this delay, and this is going to change your frequency. The frequency of your output is also going to be slightly altered each time this delay changes, and that is going to make your filter unpredictable, or the performance cannot be good because it's affecting your input signal's frequency. So that is your linear phase characteristic, very important. So what are to summarize, your FIR filter must have linear phase, causality, and your zero dominance, and finally the frequency selective property. So these are the four properties we have seen today. And now let me draw this response characteristic, because we are going to be seeing FIR filter designs. So we are going to be designing your FIR filters, and for the design of FIR filters, what are the specifications you need, or what are the parameters that you need to use to design your FIR filters, and they are these things: delta 1, delta 2, then your omega p, omega s. So omega p is my passband frequency, omega s is my stop band frequency, and the ripples you see on the top is my passband ripple. The oscillatory behavior is the passband ripple, and at the bottom you see the same oscillatory response, and that is your stop band ripples. So these ripples are unavoidable because of the Gibbs phenomenon. What happens is, whenever you go from a high to low, right, it is like jumping. So you want to jump from a top of or it's a top of a floor to the next floor, or to the bottom floor. What happens is, you have to just gear up. You have to just accelerate little bit, and that acceleration is it is going to come as a passband ripple, and then you jump, and then you're not going to go straight because of the acceleration and the ripple. You're going to go in a slanting manner, and then you land, and when you land, you're going to still you're not going to follow through with that landing, and that's going to produce this top band ripples. So this is a perfect example. You can take any accelerating body, or any body, even a ball. If you roll from the top, it is to the bottom, it will follow a slanting path, and after it falls on the ground, it's going to bounce few bounces before it comes to rest. And the same thing when it is rolling, if you want it to go a little bit further, you have to give an acceleration, and that's going to produce some ripples at the top, and also after it reaches the ground, it's going to produce some ripples. So for any free falling body, you can think about this analogy. So the same thing we are applying for FIR also. So there will be a slant, and you need a passband frequency, you need a stop band frequency, and you need a passband ripple, and you need a stop band ripple for designing your FIR filter. So you can increase or reduce these ripples, and then making it better performing. That can be done, but ripples can't be completely avoided. So now next is our FIR type. So we are now into the types of your FIR filter. So basically, we can see from these two statements that I'm making, I can have four types of FIR filters. So first one is your symmetry, which is h of n, that is equal to h of m minus 1 minus n. And then you have your anti-symmetry, which is h of 1 is equal to minus, so which means when I am talking about symmetric signals, which means my first half of the signal is equal to the second half of the signal. And when I am talking about anti-symmetry, then I am telling that my first half of the signal is equal to the minus of or the negative of the second half of the signal. And now I can have my m to be even or odd. So which means I'm going to be having four types of FIR filters, right? So it's very it's very what you can very much very small difference, because symmetry and even, that is one type, symmetry odd is my second type, anti-symmetry even is my third type, and anti-symmetric odd is my fourth type. So you have these four types, and now the only difference is, for one it is even, another one is odd, another one is you have the negative, the second half is negative for anti-symmetry. So very small difference between these types, but it is still nevertheless very important to know these types. And then why we need to know these types is because when you know these types, you can design a filter, right? You can come up with a design which is suitable for you. So mostly we go with either symmetric or anti-symmetric, and when we use this symmetry is when we want our when you're having your signal to be purely positive, right? Positive valued signal. I'm just taking for an example. I'm just saying that when my I am designing a filter where my h of n is equal to h of m minus 1 minus n, which means I want my second half to be the same as my first half, and if my first half is positive, my second half is positive, and my first half is negative, my second half is going to be negative. So that is when I go for a symmetric design, right? For anti-symmetry it is quite the opposite. If I have my first half positive, then I want my second half negative, and if I have my first half negative, then I want my second half positive. So these are the cases where we select whether we go for symmetric or anti-symmetric. Even an odd doesn't matter, to be very frank. We cannot I cannot say certain any distinctions where we may need an even, where we may need an odd, but typically we go for the odd designs, because the odd designs have what? Why we go for the odd designs? Can you tell? We go for the odd designs because then in this case your symmetry, the center of symmetry passes through a number, right? So that is very much significant, because here your line of symmetry or the center of symmetry for m equal to even passes through nowhere. It doesn't pass through any sample points. It passes through somewhat of a fractional place, right? So I prefer the odd design. I usually go for symmetric and odd. That is my first type 1 filter. That is also the most commonly used filter, or at least in my experience I have used type 1 filter I would say most in designing some noise filters for audios. I go with type 1 symmetry and n equal to odd. And like I said, for even, the only problem is the line of symmetry goes through somewhat in the middle bit. It doesn't go through a sample point, and that middle point is mostly the index will be 0.5, right? So that means you are looking at a fractional index, and then solving it or coding it becomes little more difficult. So I prefer symmetry and odd, and here these are the things I can write. But what about the phase of these two filters, type 1 and type 2? That is, they are the both symmetric filters, and here the phase for these filters are minus m minus 1 by 2. That means your phase is at the center, right? Minus of m minus 1 by 2 means the phase is at the center of symmetry. That is your phase. That is what we are talking about when it comes to the phase. For your anti-symmetry also, the phase is minus m minus 1 by 2, and we will see more on this phase and deriving these filter functions and phase response in the next class. Today I'll just introduce these 4 types of filters, and we can see the rest of these 4 types in the next class. So that is enough for today. So for anti-symmetry, what we have is your h of n is equal to minus h of m minus 1 minus n, and that is going to make the same thing. What only thing is your left half and the right half are going to be in opposite polarity. If it is plus on the left, your minus on the right, and if it is minus on the left, then you have plus on the right. The phase is going to be still minus m minus 1 by 2, but we are going to see those derivations in tomorrow's lecture. So that should be good for today's class. Thank you.